this video, we're going to learn the importance of power factor correction, the methods of power factor correction, and the capacitor size needed for power factor correction. So before we go on the topic, let's first have a review. So here is the power triangle. The hypotenuse represents for the apparent power S rated in volt ampere. The opposite is the reactive power Q rated in volt ampere reactive, and the adjacent stands for the real power P rated in watts. So the real power here is rated watts, volt times the ampere. It's the resistor. While the reactive power uses a capacitor. That's the difference between watts and volt ampere. While the apparent power is both the resistor and the capacitor. Ampere. So in reactive power, it can either be a capacitor or an inductor. So here are the formulas in obtaining power factor. So cosine theta is equal to power factor. Apparent power, or S squared, is equal to Q squared plus P squared. And here are the important notes about the power factor. So when the power factor is 0, the energy flow is entirely reactive. So if we substitute 0 here, our cosine 0 is equals to 90. So as you can see, our reactive power here is the hypotenuse, and the apparent power here, and the apparent power and the real power. When the power factor is 1, all energy supplied is consumed. So if we substitute 1 here, so the arc cosine of 1 is equal to 0. So 0. So the Q here, wala ng Q. So S is equal to P. So if you have a power factor 1, it's called the unity. And the last is the power factors stated lagging or leading to show the sign of the phase angle. So if you are given 0.8 power factor lagging, so here our cosine 0.8 something, it's lagging and leading. So in this video, we will gonna learn the importance of power factor correction. So as future engineers, we have to learn it, because in the circuit system, if the power factor is equal to 0 or nearly 0, so our circuit system will have a high reactive power. So if this means that it will draw more current, and it will draw also a high voltage, because current is directly proportional to voltage. So this results to high power consumption. If there is high power consumptions, we will have also a high cost in electricity. So if this happens in industrial companies, so the industrial companies will put the burden to the consumers. So their products will have high prices, and this greatly affects especially in the poor families. So that's why we need to learn power factor correction. So in this illustration, this is the method, one of the method in power factor correction. Bank of static capacitors connected across the load. So these capacitors are connected in delta in respect to the load. So, and this is the phasor diagram of this illustration. This is the new old angle, new angle. The apparent power, the old apparent power and the new apparent power, and the reactive power An inductive load takes a current of 60 amperes at a power of 0.643 lagging when connected to a 240 volts 60 Hz supply. It is required to improve the power factor of 0.8 lagging by connecting a capacitor in parallel with the load. Calculate the new current, the capacitor current, and the value of the power factor correction capacitor. So first, we need to put the given, the angle, no, so we need to get the phasor angle. So cosine theta is equals to 0.643 theta is equals to 50 degrees. Cos theta is equals to 0.8, and theta is equals to 36.87 degrees lagging. So since it's lagging, we have to put the under the x-axis. So we have here the 60 amps IMAX. In new current. So in A, let's solve for the new current. So how to get this new current? So let's first solve this from 0 to A. So cosine we solve for since we obtain the value of point O to A, so we can now solve for the new current. So cosine 36.87 degrees is equals to 38.57 times the new current. So 38.57 over cosine of 36.87 is equals to 48.21 amperes. Now, let's solve for the capacitor current. We have the formula I is equals to IC or yeah. So IC equals to I minus A. So we have the new current and its angle. Since it's lagging, we have the angle, negative angle, minus 60 angle. Now, after we obtain, we now can solve for the value of the power factor correction capacitor. So, IC is equal to the voltage over the reactance of the capacitor. So, X sub C or the reactance is equal to 2 pi FC 1 or we have to solve for this. So Hertz times the voltage to 40. So we obtain the value 188.2 microfarad.